All right, so let's finish up our section on number theory and modular arithmetic. So, in the last lecture, we discussed the GCD of two numbers, A and B, and we discussed the LCM of two numbers, A and B. And we discussed some of the properties that these, really they're functions of two integers, some of the properties that these functions of two integers share. And it turned out that when we were discussing the GCD and the LCM, the primary way that we thought about them in the last lecture was we thought about writing out the prime decompositions of the number A and writing out the prime decomposition of the number B and kind of comparing them in some way. And so the GCD of two integers, we thought about that by writing down all the primes in A and all the primes in B and taking the minimum of the powers that appeared. You can kind of take a look at the other video to refresh that. The point is that this is a really inefficient process. So finding the prime decomposition of large numbers is inefficient and difficult. So what I want to do today is I want to introduce a very beautiful algorithm called the Euclidean algorithm for finding the greatest common divisor of a pair of numbers that doesn't involve directly finding the prime decompositions of the pair of numbers. In all the examples that we've done so far with prime decompositions, they've been relatively small numbers that we can kind of test fairly easily, but once you get into truly large numbers, finding the prime decompositions becomes very challenging. But there is a good alternative. And what I want to express is first go over it in an example. So today we're going to discuss the Euclidean algorithm. And so I'm going to start off with the following example. I'm going to write, let's say that I'm trying to find the GCD of the two numbers 287 and 91. So what I would have done last lecture is I would have tried to find the prime decomposition of this number, find the prime decomposition of this number, and go from there. But this time, I'm going to do something different. So I'm going to begin with the following remark. I can try to divide with remainder 287 by 91. So I know by the division algorithm that there is a unique way that I can write it. And in particular, I end up with the following expression. 287 is going to be equal to exactly 3 times 91 plus 14. It's pretty easy to see that if I do 4 times 91, I'm going to get something like 360 whatever. So 3 should give me something like 273. So then 283, 287. So indeed, this works out. Okay. So remember that the GCD, the greatest common divisor, is going to be some number, the greatest number, that divides both 287 and divides 91. What I would like to remark here is that using this division algorithm statement of dividing with remainder 287 by 91, this implies that my remainder, 14, is equal to 287 minus 3 times 91. Okay. The point is, if whatever divides this number and divides this number will divide the sum of these two numbers, right? This is one of our first things that we talked about when we talked about division. So whatever the GCD is, it's going to be some number. Since it divides both 287 and it divides 91, it has to divide 14. So from this statement, what we get is that the GCD of 287 and 91, whatever this number is, it divides 14. So what I'm going to put up here is this triangle, 287 and 91 and 14. What this division algorithm is expressing is that if any number divides two of these, they have to divide the third. Any number that divides 287 and 91 has to divide 14. Any number that divides 91 and 14 has to divide 287. And any number that divides 14 and 287 has to divide 91. So even though we thought of our GCD as being between two numbers, really what we're saying is that all I need to care about is any pair of this triple of numbers. Okay, so that's already a cool statement. And what I want to do next is, since I can choose any pair of these and work out the greatest common divisor from those two, I should pick the smaller two of the pair. So what I'm saying is, the GCD of 287 and 91 is equal to the GCD of 91 and 14. Okay? And now I can repeat this procedure. So let me erase this extra step for the moment. So now, let's say I'm trying to find the GCD of 91 and 14. And let's say that I have the same idea. What I should do is I should try to divide with remainder 91 by 14. And let's see. If it were 15, it would be 1, 2, 3, 4, 5, 6. So I think that 14 goes into 91 probably 6 times with remainder. Let me check real quick off the board. 14 times 6. 4, 2, 84. Yeah, indeed. So the correct thing to write here is 91 is equal to 6 times 14, which is 84, plus 7. So now, once again, I have created a triple of numbers such that the GCD of any pair of them is the same as the GCD of any other pair. Now, I have the triangle, so to speak, of 91, 14, and 7. This expression tells me if some number divides both 91 and 14, then I can subtract this expression over to this side, and I'll see that it indeed divides 7. If a number divides 91 and 7, I subtract the 7 across, and I see that it has to divide, well, oh, maybe I made a mistake earlier. But if a number divides 91 and it divides 7, then it divides 6 times 14, which perhaps isn't as useful. So I probably made a mistake when I was talking over here with this triple. If a number divides 287 and it divides 14, it just divides 3 times 91. It doesn't necessarily divide 91. So I shouldn't take the pair 287 and 14. I should only look at the pair that looks like this or this. This pair has the same GCD as this pair. Okay, now I've said something not incorrect. So similarly, the GCD, if some number divides 91 and it divides 14, then it has to divide 7. And similarly, if a number divides 14 and it divides 7, it has to divide 91. So what we've shown here is that the GCD of these two numbers is the same as the GCD of these two numbers. Okay? So you can see that this process is repeating. Now, if I wanted to find the GCD of 91 and 14, it's the same as finding the GCD of 7 and 14. So I repeat the process. I look at the GCD of 14 and 7. And once again, I try to divide 14 by 7. And it turns out this time I can do it on the nose. So now 14 is equal to 2 times 7. So now essentially the triangle now becomes 14, 7, and 0. Because the remainder here is that 0 remainder because the division happened perfectly. So once again, we have the same result, that the GCD of 14 and 7 is the same as the GCD of 7 and 0. So the GCD of 7 and 0, the greatest common divisor of 7 and 0 is just going to be 7. Anytime that we have the GCD of a number A and 0, one can check that the biggest thing that divides A is A, and A also always divides 0. So once I get down to the step of examining GCD of 7 and 0, this is just going to be equal to 7. Notice that you probably could have done a little critical thinking and noticed what is the greatest common divisor of 7 and 14? Well, it's just 7 as well. So you can see it one step earlier than when the algorithm terminates. So the algorithm terminates at this step when I have the GCD of some number and 0, and then I just take that number. So tracing back through, the GCD of 0 and 7 is 7. It's the same as the GCD of 7 and 14. That's the same as the GCD of 14 and 91. And that's the same as the GCD of 91 and 287. So at the end of the day, this answer, what is the greatest common divisor of 287 and 91? It's 7. The important thing about this algorithm, well, there are many important things about this algorithm, but one good thing is that from a computational standpoint, adding numbers and adding and subtracting numbers, which is really what we're doing here, is easier than factoring numbers. Factoring numbers is a difficult process computationally. Okay, so this is the idea of the algorithm. It's a beautiful way to find the GCD of two perhaps larger numbers than you can find the prime factorizations of. It's still possible to do. And it depends on always writing these relationships according to the division algorithm, where I start with two numbers, I try to divide them with the remainder, and it turns out that the GCD of this pair of numbers is the same as the GCD of this pair of numbers. Sorry about the error that is now preserved for any place that ever tries to hire me. Okay, let's continue. So this example pretty much gives you the idea of what's going to happen. And I just want to discuss kind of the general overarching proof now more symbolically than with the example. So we're going to start off with the following lemma, which says something that you all will expect. Let A be equal to BQ plus R with 0 less than or equal to R. Sorry, I should put D. Less than or equal to D, as in the division algorithm. Then we have the following property, that the GCD of A and D is equal to the GCD of D and R. Okay? So the way that we're going to show this, so remember, by definition, the GCD is the largest number that divides both of the arguments. So to show that the greatest possible number that divides both of these arguments is the same as the greatest possible number that divides both these arguments, what we're going to show is that any number that divides this number, and any number that divides this number, divides this number. Essentially, this is saying that how do you check that two numbers are the same? You check that they have the same prime factorizations. And prime factorization tells you exactly when can you divide. So if two numbers are different, there is some difference in their prime factorization, and that means one of them is divisible by something and the other one isn't divisible by that thing. So to prove this, we show that if D divides the GCD of A and B, or A and D, then D divides the GCD of D and R. So that'll show whatever divides this, and whatever divides this, divides this. Okay? And vice versa. So assume that D divides the GCD of A. Oh, shoot, I'm using D's in two different places. I'm sorry. Let me do X, say. X an integer. I'm sorry. So here I'm taking X to be an integer, kind of bad. So I am assuming that X divides the GCD of A and D. But dividing the GCD of A and D means dividing some number that divides A and dividing some number that divides D. And by the fact that if A divides B and B divides C, then A divides C, what we see is that X must divide A and X must divide D. X divides A and X divides D. What I now want to show is that if X divides A and X divides D, then X divides A minus Q times D. This is our first theorem on divisibility, which we're using over and over again. If I have X dividing one number and X dividing another number, then it divides sums of those numbers and divides, if X divides D, then it divides any integer times D, and then it divides this sum. Then X divides A minus Q times D, so X divides, well, what is A minus Q times D? It's exactly R. So if I started off with a number that divides the GCD of A and D, I know that it divides A, I know that it divides D. This argument shows that it divides R. So now X divides D and R. If X divides D and X divides R, then it's going to have to divide the GCD of D and R, right? The GCD of D and R is the biggest number that divides D and R. But if I have some number which I know divides D and R, maybe it's not the biggest, but it will divide the GCD. Then X divides the GCD of D and R. This is once again falling back on the fundamental theorem of arithmetic and factoring things into primes. Okay, so what I've shown is that if there's some number that divides this number, then it divides this number. And this argument works exactly in the other direction. If I pick some y, well, I'll just do it. Now assume So we need to show the other direction. Now assume y in Z divides, such that y divides GCD of D and R. Then y divides D and y divides R. But if y divides D and y divides R, then y divides D times Q plus R for any integer Q. So y divides A. And if y divides A and y divides D, since y divides A and y divides D, y divides the GCD of A and D. And that shows the other direction. If I have something that divides this number, it also divides this number. Essentially, this argument is just saying exactly what is encoded in these triangles. The GCD of the top pair is the same as the GCD of the side pair in all these triangles that we make that are built up from the division algorithm. Okay. And so now all that really remains to be done is to write down the formal procedure for the division algorithm. I suppose I'll lift up this one. So now, let's suppose that A and B are positive numbers, such that, let's say, without loss of generality, A is greater than B. Then what we do is we set R0 is equal to A, and R1 is equal to B. And then we just run the division algorithm. So the division algorithm says I can always find R0 is equal to, say, what do I want to write? R1 Q1 plus R2, where now R2 is greater than or equal to 0 and less than R1. Right? So I've reduced by one step. So now I write the following, that the GCD of R0 and R1 is equal to the GCD of R1 and R2. Okay? Now I repeat this step. Now I start over with R1. This is going to be equal to R2 times Q2 plus R3, where once again, 0 is less than or equal to R3 is less than R2. And I add on to the equality of the GCDs. Now the GCD of R2, or of R1, R2 is equal to the GCD of R2, R3. This is all using the lemma that I have hidden behind this board, unfortunately. I can unhide it. This statement, when I'm adding on, or when I'm setting these GCDs equal, that's just using this statement again. And we repeat. Guess what? R2 is equal to R3 times Q3 for some Q3 plus R4, where 0 is less than or equal to R4 is less than R3. And I get another equality. The GCD of R2 and R3 is equal to the GCD of R3 and R4. Okay. The first thing to note is the following. It looks like this set of equalities could continue forever. That is, it looks like I could maybe potentially find an infinite number of R's such that this process would never stop. But that's actually not the case. The point is that I always have this decreasing property. R1 is some positive number, and R2 is less than R1. And then R3 is less than R2, and R4 is less than R3, and so on and so forth. Moreover, these numbers are bounded below by 0. So that means I'm taking some set of numbers that are bounded above by R1, or maybe potentially bounded above by R0, and they're bounded below by 0. And there's a property, actually an axiom of the integers called the well-ordering principle, which essentially says that if you build a collection of integers in this fashion, you're going to have some lowest integer. What that process translates to is that this algorithm eventually terminates. That is, eventually, we're going to get all the way down until the point where we have something that looks as follows. We're eventually going to get an R, let's call it n minus 1. And this is going to be equal to an R n times Qn, such that at this stage, there's going to be no remainder. So when we did our example, we hit this when we were looking at 14 being equal to 7 times something with no remainder. And at this point, the process is about to terminate, right? So here, since Rn minus 1 is equal to Rn times Qn plus 0, all the way over here, I'm going to have equality equal to GCD of Rn minus 1, Rn. This is going to be equal to the GCD of Rn, comma 0, which we just know is going to be Rn. So this is the Euclidean algorithm. We start with 2 positive integers, and we produce this long chain of remainders, such that at each step, the remainder is going down. And at the end, I'm going to get a remainder of 0. And at this point, we have found kind of the last actual number, which is the GCD of this term, which equals all of the GCDs that came before. So we find the GCD of our original pair. Yes, this would be a great time to ask for questions. Let me do one thing for a second. Okay, so after having discussed this process of the Euclidean algorithm, I just want to do one more example, so we're comfortable with just doing it again. Okay. So let's do the following example. Let's find the GCD of 1,331 and 1,001. Okay? So once again, the thing that we're going to apply again and again is the division algorithm. So the first thing that I'm going to do is I'm going to write 1,331 as being equal to, well, only one of these, 1 times 1,001 plus 330. Is that math correct? Yes. So in essence, what I'm doing is I'm writing my first triangle, 1,331 and 1,001, and then my remainder is 330. I know once again that the GCD of this pair is equal to the GCD of this pair. And now I repeat so this is my R0, this is my R1, or this is my R1, and this is my R2. And now I repeat. I start with 1001, and this is going to be equal to 3 times this thing. 3 times 330, right? That's going to give me 990, plus 11. So once again, I should label in a different color. This is my R1, this is my R2, and this is my R3. And I have another triangle that looks like 1001, 330, and 11. So the GCD of these two numbers is equal to the GCD of these two numbers. Next, I repeat the process. I have 330, which is my R2. I want to think about how many times is this divisible by 11. Well, I think it's actually perfectly divisible by 11, because 11 times 3 is 33, and then I just multiply by 10. So 330 is equal to 11 times 3 times 10. This is my remainder, plus 0. Okay? So this is my R2, this is my R3, and this is my R4, which is 0. So I have another leg of the triangle, 330, 11, and 0. The GCD of 330 and 11 is the same as the GCD of 11 and 0. And now, just to be very pedantic and do the very last step, I have the GCD of 11 is equal to 11 times 0. Wait. No. This is quite bad. Once I have that I am looking for the GCD of 11 and 0, though, I know that this is just 11. So thus the GCD of 1331 and 1001 is equal to the GCD of 1001 and 330, which is equal to the GCD of 330 and 11, which is equal to the GCD of 11 and 0, and this we know to be equal to 11. So the GCD of these two numbers is 11.